talk about spontaneity of redox reactions. So if you recall, in the thermodynamics chapter, we talked about what makes our reaction or process spontaneous. And it comes down to the sign of delta G, the free energy. If delta G is negative, then the reaction is spontaneous. If delta G is positive, that means the reaction in the direction it's written is non-spontaneous, and spontaneous in the reverse direction. So what we're going to talk about is how what we have learned so far ties into predicting the spontaneity of electrochemical reactions. So firstly, I want to introduce to you this equation. This equation relates the free energy of a reaction in a cell to the standard EMF, or the EMF of the cell. Delta G is equal to minus N times F times the EMF of the cell. And correspondingly, as far as standard conditions are concerned, we can calculate the standard free energy based on the free energy, or I should say the EMF standard of the cell. So as you can see, the equations are almost identical. The only difference is that this equation here describes what happens under standard conditions, all right? Now, just to identify the different terms in these equations, N represents the number of moles of electrons involved in the reaction, right? So we're talking about the total number of electrons represented in the redox equation that is transferred from the substance being oxidized to the substance being reduced, all right? F is a constant known as a Faraday's constant, and it has this value. It represents a charge carried by 1 mole of electrons, right? So as you can see here, it's expressed in this way. You'll notice the units here says coulombs per mole. So it's 96,500 coulombs per mole. So 1 mole of electrons will carry this much charge, right? So that's called the Faraday's constant. Now, we already met this equation here. Delta G standard is equal to minus RT ln K. So if delta G standard is equal to this, and delta G standard is equal to this as well, that means that this expression must be equal to that expression, and therefore we can rearrange it to get an equation relating the equilibrium constant to the EMF standard of the cell, all right? And of course, we know that R is a constant, F is a constant, and if we're talking about standard conditions, T is a constant, which is 298. So if I put in the values for these constants into this equation, then we're going to end up with this, well, this is just showing you the units canceling. All the units will cancel, excepting the volt unit. So you're going to end up with this right here. The standard EMF of the cell is equal to 0.0257 volts over N times the natural log of K. And if we instead want to use the log to the base 10 of K, then this expression changes to what you see here, right? So these two are basically representing or saying the same thing, all right? You can use either one of them to calculate the standard EMF of the cell if you know what the equilibrium constant is, all right? Okay, so basically what we have covered so far is the relationship between delta G standard, the EMF standard for the cell, and the equilibrium constant for the reaction in the cell. So basically this shows you the relationship between delta G standard and the equilibrium constant. This is what we met before in the thermodynamics chapter. This is what we were just introduced to a while ago. Delta G standard is equal to minus NFE standard of the cell. And then this equation here relates the EMF of the cell to K. And this is basically as a result of the relationship between these two equations right here, right? So basically we can use, these equations here to solve for different things, depending on what the question is asking for, and what you're given in the question, all right? So, to summarize what we have just learned that basically for a reaction to be spontaneous, delta G has to be negative, which means that K must be greater than 1. And that is clearly what you can basically, the conclusion you can come to based on this equation right here, right? Delta G is negative, K is greater than 1, which means correspondingly that the EMF of the cell must be positive, right? So basically under those conditions, what this tells you is that the products will be favored in terms of their formation, all right? So basically, in order for the products to be favored, delta G would have to be negative, K would have to be greater than 1, and the EMF of the cell would have to be positive. Now, if delta G is equal to 0, what that tells you is that the reactants and products are equally favored. Correspondingly, that means that K must be equal to 1, which makes sense, because if K is equal to 1, ln1 is 0, which means that delta G standard is 0, and also, correspondingly, the standard EMF of the cell would be 0 as well, right? On the other hand, or the third item here, if delta G is positive, which means that the reactants are favored, not the products, that means that K must be less than 1, which means that the standard EMF must be negative, all right? So that's basically a summary of the relationship between the standard free energy, the standard EMF of the cell, and the equilibrium constant of the reaction involved in the cell. Okay, so the next slide will be an example based on what we have just covered. So this question says, what is the equilibrium constant for the following reaction? And it gives you the equation right here, all right? At 25 degrees, so implying standard conditions will apply. Okay, so the first thing I would write down is the relationship between the EMF of the cell and the equilibrium constant. The aim is to find K, right? Now, what we need to do, of course, is to find a couple of things. We need to know what N is, and we need to know what the EMF of the cell is. So the best way to figure that out is that we write down the half equations, which when added will give you this net equation right here. So one half equation would involve the oxidation of the silver to form silver ions. So that's a half equation right there. And the reduction equation would be where Fe2 plus is being reduced to form Fe, right? Of course, we need to find N, and this equation tells you, or these two half equations tells you what N is. N represents the number of electrons lost and gained, right? So that's the first thing we can say. We can say that N is equal to 2, right? Now, the next thing we need to do is find out what the EMF of the cell is. And in order for us to do that, we'd have to consult the tables I made reference to earlier to find the standard reduction potential of both the silver electrode and the iron electrode or half cell, right? So basically, the standard EMF would be the EMF of the reduction half of the cell minus the EMF of the oxidation half of the cell. And we put the numbers in. And of course, after consulting the tables, as I said before, and when we do that, we get the standard EMF being equal to 1.24 volts. So that would go here, all right? So we plug in the value for the standard EMF and the number of electrons transferred into the equation, but of course we have to rearrange it to solve for K. So when we rearrange this to get an expression for K, we're going to end up with this equation right here, and all we have to do is put the numbers in. So basically we put the minus 1.24 times 2 divided by the 0.0257 volts, and we solve for K, and we find that K is equal to 1.23 times 10 to the minus 42, all right? And that's basically how we would solve this problem, all right? Okay, one last thing I want to cover before I sign off on this video, and that is the effect of the concentration on the cell EMF, all right? Now, another expression I want to introduce to you is this expression right here. Delta G is equal to delta G standard plus RT ln Q. And just to remind you of what Q is the reaction quotient, which is basically the concentration of the products divided by the concentration of the reactants at any time, not necessarily at equilibrium, all right? Now, we know already that delta G is equal to NFE, and delta G standard is equal to NFE standard, right? So if we plug in this expression where delta G is, and this expression where delta G standard is, you're going to end up with this expression right here, and we can rearrange this to solve for E, which is equal to standard EMF minus RT over NF times ln Q. And this equation, as you can see here, is called the Nernst equation, all right? So at 298, which is Kelvin, which is standard temperature, if we're thinking of standard conditions, then E would be equal to 0, all right? And T would be equal to 298 Kelvin. R, of course, is a constant, F is a constant, and N, of course, is the number of electrons transferred. And I misspoke. E would not be equal to 0 at that point, but we can find out what E is based on the 298 Kelvin that you're going to place here. R would be equal to, in fact, let me just show you what the result would be. R would be equal to 8.31. F would be Faraday's constant. And if you plug those numbers into this, you're going to get this equation right here, right? Where E is equal to E0 minus 0.0257 volts over N times ln Q, all right? Another way of expressing it is this way right here, where if instead of natural log, you use log to the base 10, then you're going to get a different value for the constant here, 0.0592 volts. Everything else would be the same, all right? So we call this a Nernst equation, which is basically showing you the relationship between the EMF of the cell and the reaction quotient. Now, one thing I should mention here is that if, let me make a note of it here. Oh shoot, I can't. Unfortunately, I cannot make a note of what I want to write down here. In fact, let me get out of this here and go to my writing tablet here, because one thing I think I need to show you is what happens if Q is equal to K. So what I'm going to do here is rewrite the Nernst equation, which is E, which is equal to E0 minus RT over NF ln Q, all right? Now, what I meant to say earlier is that if Q is equal to K, which is the equilibrium constant, that means that E would be equal to 0, right? So if E is equal to 0, that means that 0 is equal to E0 minus RT over NF ln K. And therefore E0 would be equal to RT over NF ln K. All right? Which is what we saw earlier, right? If you go back to, in fact, let me show you. If I go back to a previous slide, right? This shows you the relationship between E and ln K, right? So basically, I'm just proving this part here to be true, all right? Based on what we said about the relationship between the Q, reaction quotient, and the E here, and the fact that when Q is equal to K, E is equal to 0. Okay, so much for that. Let me go back to the PowerPoint and see what I need to talk about next. Okay, so let's move on to this example right here, and then we'll call it a day. So this question, it's an example, says, will the following reaction occur spontaneously at 25 degrees if the concentration of Fe2 plus is 0.60 m and the concentration of Cd2 plus is 0.010 m, and it gives you the equation for the cell reaction, all right? So the first thing I would do is recognize that the question is asking for delta G, right? And basically what we need to do is find out if delta G is positive or negative. Or we could use something else. We could use the standard EMF or the EMF of the cell. If the EMF of the cell is greater than 0, that means that the reaction is spontaneous. If the EMF of the cell is less than 0, the reaction is non-spontaneous. So it's a matter of convenience which you choose. You could also try to find K, right? The one that would be more convenient, in my opinion, would be the EMF of the cell, because we can use the Nernst equation. But before we do that, the first thing we need to do is identify the half equations for this reaction. So one half equation would be the oxidation half equation, where the cadmium is undergoing oxidation to form the cadmium 2 plus ion. And the reduction half equation would be where the Fe2 plus is undergoing reduction to form the Fe, all right? The number of electrons transferred would be 2, all right? So that would be the N in the Nernst equation, right? What we also need to find is the standard EMF, all right? And of course, to do that, we have to consult the tables, and we look up the standard EMF of the iron half cell and that of the cadmium half cell, And remember, it's always the reduction half cell minus the oxidation half cell that determines the EMF of the cell itself. So you look up those values and we plug them into that equation, and we're going to end up with the standard EMF in this case being equal to minus 0.04 volts. Then we go to the Nernst equation, which is this right here. So now we have the standard EMF and we have the N. The only thing we need to find out now is what Q is. And remember, Q is the reaction quotient, which is equal to this right here, right? It is the concentration of the CD2 plus. In fact, unfortunately, I can't write it down again. By the way, it's the concentration of the CD2 plus divided by the concentration of the Fe2 plus, right? So that's 0.010 divided by 0.60. So that's what we have here. And that will go where Q is. So we plug it into this expression here. And then we do our number crunching to find out what the EMF is, right? And it turns out that the EMF of the cell is equal to 0.013 volts, which is obviously greater than 0, which means that this reaction, given these concentrations, will be spontaneous. All right, so that's basically how that is done. All right, so we're going to stop here for today. And the next thing we're going to talk about, we're going to go through some examples of actual cells or batteries that are used to produce electric current. And then we move to some other things as well, such as electrolysis, which is the other type of electrochemical process that we'll be concerned with in this chapter. Okay, until next time.